All right, we're going to solve now a 3x3 linear system of differential equations. And once again, we'll use the eigenvector method for this. Now, because it's 3x3, it's going to be a lot more work than the previous example. So the first step of this, of course, is still taking our determinant of a minus lambda I and setting it equal to 0 to get the eigenvalues. So that's the same thing as taking lambda off of the main diagonals and keeping the other entries the same. All right, now because this determinant is 3x3, the best way to approach it is to use cofactor expansion. And the idea here is to find the row or column with the largest number of zeros in it. And in this case, we could either take the top row or the middle column to do this. But in this case, we're going to go through and do the top row just because rows are a little easier to follow visually. So the idea is to now expand on this row. And to do so, we take the first number, which is -3 minus lambda. And now that is multiplied by the subdeterminant created from striking out that row and that column. So it's just these numbers here. So that's going to be 3 minus lambda, -12, 2, and -6 minus lambda. In our next row, we're going to have a 0. And normally with determinants, the signs alternate. The first term is positive, the second one is negative, and so on. So it's technically a opposite here because of its position. But once again, there's a 0 there as the entry, and it doesn't matter what's inside of the 2x2 matrix because that 0, of course, is going to cancel all that out. And then in the last spot, we have our +2. And then that's going to be times the subdeterminant from, again, striking out that row and that column. So now we're going to look at just this 2x2 matrix, which is going to be 6, 3 minus lambda, 2, and 2. We now go through and start multiplying this out very carefully because mistakes here can throw everything way off. So that's -3 minus lambda times 3 minus lambda times -6 minus lambda, and then plus 24, the product along the back diagonal subtracted. And then that's going to be +2 times the 6 times 2, making 12, minus 2 times 3 minus lambda. All right, now we have to go through and start carefully multiplying this out. It's always a good idea to keep that middle or that front leading factor kind of separate for now and to simplify inside of the parentheses. So that's 3 times -6 makes -18, minus 3 lambda plus 6 lambda plus lambda squared plus 24. And then back here, that's 2 times 12 minus 6 plus 2 lambda. And we just keep on multiplying this out. -3 minus lambda. Inside parentheses, that's lambda squared plus 3 lambda. And then 24, take away 18, of course, is plus 6. And then back here, that's 2 times parentheses, 2 lambda plus 6. Now, at this point in the problem, it's a little hard to see, but you will notice that that first factor and that final last factor are actually common because in the first one, we can factor out a -1. It leaves us with lambda plus 3. And then in the back, we can actually factor out a 2, and that 2 will get together with the other 2 to make 4, and what you're left with is lambda plus 3. So both of these terms here have a common lambda plus 3 that you can factor out of them. So when you do that, you're going to have a lambda plus 3, but now that's multiplied times the -1 that's still in front times the lambda squared plus 3 lambda plus 6. And then back here, when you pull out the lambda plus 3, there's a plus 4 behind it. So this is lambda plus 3 times negative lambda squared minus 3 lambda minus 6 plus 4. And that factors into lambda plus 3. And then negative lambda squared minus 3 lambda minus 2. So that's actually going to be, if we factor out a negative lambda plus 3 times lambda plus 2 times lambda plus 1. And as you can see, we are now ready to find our eigenvalues because this whole time, this was equal to 0. So our eigenvalues are -1, -2, and -3.